All right, in this video, we are going to tackle part 2 of the first semester review. So let's go ahead and do so. A lot of derivatives on this part using all the derivative rules that we've learned in the first half of the year. So starting with this first one, first thing that you would want to do is rewrite this as a rational exponent power, x squared plus x, and this would be the 1/3 power. So then from here, we would do actually the chain rule. Tells us to bring the 1/3 in front, keep the inside the same, subtract 1 from that power, makes it negative 2/3, and then multiply by the derivative of the inside, which would be 2x plus 1. That would be okay for right now. On the AP test, this probably would be rewritten as a fraction, like so. Anything with a negative exponent would go to the bottom, so that 2x plus 1 would stay on the top. And on the bottom, you would have 3 times, it would be the square root, because its top is the power, or sorry, top is the power, so it means the cube root of x squared plus x quantity squared. That's how I'd write it. So both of those would be good, but again, on the AP test, it might be written that way. Next one's a little bit easier. Find this derivative, again, using really as a combination of the chain rule and the power rule. We bring the 6 down in front for y prime, keep the inside the same, subtract 1 from the exponent, and then multiply by the derivative of the inside, which is 2x plus 2. And we'll leave it like that for now, it's fine. For the next one, the derivative here, we need to use the product rule because we're multiplying two things. So y prime would be the derivative of the first thing, which this is the same as the 1/2 power. So 1/2 times 2x plus 1 to the negative 1/2 power. So that's the derivative of the first. It's like f prime times the second function, which we call g, x cubed. And then it is plus fg prime, so the original first, 2x plus 1 to the 1/2 power, times the derivative of the second, which is 3x squared. And we'll just leave it like that for now. The next one, position equation for the movement of a particle is given by this function s here, where s is measured in feet and t is measured in seconds. Find the acceleration. So I believe I told you in the introduction video, the acceleration is the second derivative of position. So we need to find the second derivative, and then we're going to plug in 1 because it's at 1 second. So first derivative, which we call s prime, that is equivalent to the velocity function v of t. So for that, we're going to use a chain rule. Bring the 2 in front. Times t to the third plus 1 to the first power now, times the derivative of the inside, which is 3t squared. Might just simplify that a bit before we take the derivative again. Make it just 6t squared times t to the third plus 1. I suppose you could actually even multiply that through if you want to, so that you wouldn't have to do the chain rule again. Might make it even easier. Just go ahead and distribute that through. Comes 6t to the fifth plus 6t squared. And then s double prime, which is equivalent to a of t, would then be 30t to the fourth plus 12t. And our last step then is to plug in 1. So a of 1, which would be 30 times 1 to the fourth, plus 12 times 1, which would just be 42. And that is going to be measured in feet per second squared. If it was velocity, it'd just be feet per second. But since it's acceleration, it's units squared, so feet per second squared. For number 25, so let's take the derivative of this. dy dx is just another way to represent derivative. So this uses the quotient rule. So y prime would be the derivative of the top, which is just 1, times the bottom. Oh, sorry, I didn't see that y down there. That y down here, sneaky here, tells us this is actually implicit differentiation. Doesn't say it in this problem, but that is what you need to do. because the y isn't by itself. So let's go ahead and do that. Makes it a little bit more challenging. So the derivative of, remember when you do implicit differentiation, you take the derivative of everything. Anytime you take the derivative of a y, you just gotta throw a y prime on there as well. So the derivative of y is y prime. Now this, we still do need to use a quotient rule. So it's gonna be the derivative of the top, which is 1, times the original bottom, minus the original top, x, times the derivative of the bottom. Well, the derivative of the bottom would just be derivative of x is 1. The derivative of y would be y prime. So 1 plus y prime over x plus y quantity squared. Now at this point, what we need to do is get the y primes on one side by themselves. So first step in doing that, let's see here. I'd want to get rid of that fraction. So let's make this y prime times x plus y quantity squared, just multiply it over, equals, and just simplify this top a bit. Oh, whoopsies. That 1 on the top just gets multiplied through. So it just becomes x plus y. And then this becomes minus x minus xy prime. So then we can group all of the y primes on the left side by just adding that over. Let's see, continue it down here. So we got y prime times x plus y squared plus xy prime equals, and looks like this one actually missed here, x and minus x cancel, so equals y. We then want to pull out the y prime from these two terms, so we're left with y prime times x plus y squared plus x equals y. So then finally, y prime is just y divided by all that, x plus y squared plus x. So that one takes some effort to get, but that is how you would solve it. All right, the next one is another implicit differentiation. So this one, dy dx would then be derivative of x squared is just 2x. This one requires a product rule, so plus the derivative of x is just 1, so it's just 1y plus xy prime plus 2y y prime. So remember, whenever you take the derivative of the y, you got to throw a y prime on it. We then group the y primes and factor it out. So we're going to have y prime on the left side. When we factor that out, we're left with x plus 2y. And then moving the other two terms over, 5 minus 2x minus y. And then divide there. So y prime is 5 minus 2x minus y divided by x plus 2y. Right. The next one, we're also going to be using implicit differentiation. It's supposed to find the slope of the curve. So think derivative when you see slope of this equation. It's got extra y's in there, so we know we're going to be doing implicit differentiation. And then we're just going to plug that point in when we're done for x and y. So let's go ahead and find the implicit derivative yet. First, I'm sorry. So this becomes 4y to the third y prime minus the derivative of x is just 1, so it's y squared. Let's do this. Minus y squared plus x times 2y y prime equals 1. All right, let's make some sense of this here and distribute that negative sign. Let's keep this 4y cubed y prime minus y squared minus 2xy y prime equals 1. So then solving for y prime, and then be 4y cubed minus 2xy. And we would add the y squared over, so 1 plus y squared. and then divide. So y prime would be 1 plus y squared over 4y to the third minus 2xy. Now we can plug in that point, 1/2 comma 1. So y prime would be 1 plus 1 squared over 4 times 1 to the third minus 2 times 1/2 times 1. We get 2 on top. On the bottom, we get 4 minus, looks like 1. So 2 over 3. All right. It's a pretty intense problem, but that is one that you could definitely see on the AP test. All right. The next two are what we call related rates problems. Let's maybe move 28 down here. So for 28, radius of a circle is increasing at the rate of 5 inches per minute. So I'm going to call that dr dt. That's the rate. That's the keyword rate of increasing. And it's a radius. So it's dr dt equals 5. At what rate is the area increasing? So that means we want to find dA dt, the rate of the area increasing, when the radius is 10. So that's the information we know. Obviously, this is going to be an area formula, right? Because it's talking about area. So just think about the area of a circle. Area is pi r squared. We don't want to make any substitutions yet because all the variables are changing. There's no not changing variables, if you will. So we want to go ahead and differentiate first. The derivative of a is dA dt equals pi is just a constant, so you don't have to do like a product rule there. It's just a constant. It's like 3.14, right? So just think of it as that. So this just 2 comes down and multiplies 2 pi r dr dt. We then just plug in the stuff that we know. So then it's just 2 pi times 10 times 5, which is just 100 pi, I believe. Yeah. We'll just leave like that 100 pi, and it's a rate of a radius changing, and that is feet per minute. 100 pi feet per minute. Right. And number 29, let's go and do that one next. Gives us our formula. It says that air is being pumped into it. So if air is pumping in, that means the volume is changing. So that's dV dt. 28. What rate is the radius changing? So we want to find dr dt when the radius is 3 feet. So when r is 3. So very similar, except it's just going to be on the other side of the equation. Start with v equals 4/3 pi r to the third. Differentiate. It would be dV dt equals, the 4/3 pi is just all one constant. So the 3 multiplies down there in front. 3 times 4/3 pi r squared dr dt. We then can go ahead and plug in. dV dt was 28 equals, these 3's cancel. So 4 pi r squared is 3 squared dr dt. So then just solve for dr dt. That would be 9 times 4 is 36. So it's 28 over 36 pi dr dt. So whatever that is, that would be your answer. I guess we could reduce it at least. 4 goes into both of those. So 7 over 9 pi. And that is in feet per minute. And actually, I just thought about the last one. That was a dA dt, so that should be feet squared per minute. Volume is cubic. Area is squared, so it should be feet squared. But on 29, we're finding the radius. Rate of the radius is changing, so that's just going to be feet. Okay, let's move up to number 50, the horizontal asymptote. So whenever you see horizontal asymptote, what you want to think is the limit as x goes to infinity. Up to x squared plus x minus 7 over x squared minus 1. From this point, there's actually a really easy, simple way to figure this out. That is, you're just looking at the highest powers. There was 3 different rules. If the highest powers are the same, which these are, they're both x squareds, then it's just simply y equals the ratio of the leading coefficient. So it's just 2 over 1 or 2. So y equals 2. The next one, it's just saying the limit as x goes to infinity. So it's just kind of the next step. However, we have this square root down here. So when we look at these, if you compare them, it looks like they're both x squareds. However, on that bottom, that would actually become just a first power because we got this invisible 2 out here. So the bottom is really only a first power when you use that square root. If it had been 4x to the 4th, then they would be the same power. And then you would take the square root of the bottom for the coefficient. So if this had been like square root of 4x to the 4th over x squared, then the answer would be the ratio of leading coefficients, which would actually be 1 over 2. However, that's not the case. It's an x squared, which means the bigger power is on top. That tells us that it's just going to go to infinity, and there are, well, there would be no horizontal asymptotes. So when we plug it in, it would be definitely going to go to infinity because the top would grow faster. And it is positive infinity, so it would be like a positive infinity squared, right? And that's going to grow bigger. The bottom would be 4 times infinity squared minus 1. That's going to be a positive over a positive, so it would go to positive infinity. If the top had been like a negative x squared, then that would be a negative over a positive, and that would take it down to negative infinity. All right, and then we close it out with some derivatives, some trig, exponential, and logarithmic. Let's start with A, the derivative of f prime of x. A lot of these are going to use the chain rule, where we got stuff inside of those cosines and sines. So the derivative of cosine is minus sine. We keep the inside the same, 4 pi x cubed. And then times the derivative of the inside. 4 pi is a constant, so it just becomes 4 pi times 3, which is 12 pi x squared. It's the derivative of the first thing. Plus, derivative of sine is cosine. Keep the inside the same, x plus 2. And then times the derivative of the inside, which is just 3. And we'll just leave it like that for now. Okay, B. This is going to use a product rule. So b prime of x. Derivative of x to the 4th is 4x to the 3rd. Keep the original second term. Plus the original first, x to the 4th. Times the derivative of the second. Derivative of cosine is minus sine of 3x squared. Times the derivative of the inside, which is 6x. And again, that's okay for now. Suppose you could rearrange this if you wanted to as like plus, actually it'd be minus 6x to the 5th sine of 3x squared would be how you'd rearrange that. The first part, there'd be nothing to do. All right. C. This is E, the exponential, base exponential. So this is theta is the variable, that's a theta. So y prime of theta is going to be derivative of e to the anything is e to the u times u prime. So it's going to be e to the secant of 2 theta times the derivative of 2 theta. Remember the derivative of secant is secant x tan x. So the derivative of this is secant of 2 theta tan of 2 theta times the derivative of 2 theta, which is 2. So that would be our answer. Again, you could rewrite that. D, natural log function is 1 over u times u prime. So it's going to be 1 over that whole function times the derivative of that function. So k prime of x will be 1 over all of that, 7x squared plus sine x plus 1. times the derivative of the bottom, which is 14x plus derivative of sinus cosine x. The 1 goes away. So you could also just write that on top. For E, I guess I deleted E. Sorry, for F, go over here. This is going to require a quotient rule. So it's going to be h prime of x, derivative of the top, which is 16x minus 7, times the bottom, cosine of 2x, minus the original top, times the derivative of the bottom. Derivative of cosine of 2x would be sine of 2x times 2 over the bottom squared. And I'm not going to reduce that. That's okay for now. G, m prime of x. We'd want to just first write this as x to the 1/2 power. In this one, you want to write as x to the negative 4/3 power. So then it would become 1/2 x to the negative 1/2, and then minus 4/3 x to the negative 7/3. Your solution. You could also rewrite this as 1 over 2 times the square root of x minus 4 over 3 times the cube root of x to the 7th power. For h, that is going to require a quotient rule. Q prime of x, derivative of the top, e to the x is just e to the x, times the bottom, 1 plus x squared, minus the original top, e to the x, times the derivative of the bottom, which is just 2x, all over the bottom squared. Leave it there. And last but not least, I there. This is a chain rule because we have something inside of the cosine. So the derivative, your n prime of x. Derivative of cosine is minus sine of u, so the tangent stays inside. Tangent of x times the derivative of tangent of x, which is secant squared x. And that is our solution. All right, I know it's kind of an intense review. Took a long time probably, but there's a lot of stuff on the AP test, and we'll just keep chugging along and doing our best. As always, reach out to me if you have questions.